Okay, welcome everybody. This is the sixth PLUMED Masterclass of this second series. It's a great pleasure for me today to present these speakers. We don't have one speaker today, we have two, both from if I'm not mistaken, from the state of New York, at least live from the state of New York. One is Andrew White, from the University of Rochester, so a bit north, upstate, you say. And instead from the center of Manhattan, from New York University, Glenn Hockey. And they will share this space today and talk about different things. And thanks for being here. Thanks for accepting to give this masterclass and for coordinating between the two of you to give this lecture. So I think Andrew will start, and the floor is yours. Thank you.
Thank you. I'm excited to be here to talk about this. So Glenn and I have been working on a method for almost, God, I don't know, 8 years or something like this, is when we first started working on this. And it's called experiment-directed simulation. And I'll talk a little bit more about the nomenclature and then how this works. And then Glenn will talk a little bit about how you can use this in coarse graining. I have some very introductory slides here. They look cool, so I like to include them. So when we're doing a simulation, it's when we start from the potential energy of molecules or of atoms, and then we go and get some ensemble properties. So this is just Leonard-Jones. It's just showing how you can see different behavior when you go to the simulation. And we can quantify this with statistical mechanics. And what's really nice about running molecular dynamics is that even though we know that the probability of any configuration is the Boltzmann distribution, which is a little bit complicated to compute analytically, when we run molecular dynamics, we just sample directly from it. So we don't need to compute this exponential. And we can just take an arithmetic average to compute the expected value. And so in PLUMED, what we do is we have collective variables, which are typically functions of the positions, so some f of r. And then in this module, what we're thinking about is how to connect some collective variable of a simulation with some experimental data. So throughout this talk, I'll be saying things like an observable, and an observable is a collective variable which we can also measure in an experiment. And because when we think about molecular dynamics, we think about simulation, statistical mechanics, we're always thinking about an ensemble. And so we're thinking about an ensemble average. So we want to connect the expected value or the ensemble average of these observables with experiments. And we know from statistical mechanics that the observable average is equal to the integral of the probability of that collective variable. And like I said, in simulation, that's just the arithmetic average. So what happens if we don't have an agreement? That is, we have some, oh, I'm sorry, this probably shouldn't be this equation, but if we have some measurement and that measurement doesn't agree with the ensemble average. So what do we do if we don't have agreement? So for example, if we measure chemical shift in an experiment and it doesn't agree with what our simulation shows, or we know the radius of gyration of a protein, or we know the something like the number of hydrogen bonds, if any time we have disagreement, how can we fix that? So I'm going to give like a motivating example. Just think in your minds about, what do we do when we have this disagreement? And we'll get some concrete examples so that we can see how this works. So peptides are the system we're looking at. So peptides are just small proteins. So coming from 20 amino acids, we like peptides because they have charge groups, aromatic groups, nonpolar, so we can look at a lot of different chemistries. So they're kind of a fun system to simulate. If any of you are doing biological simulations, then you're already aware of it. One of the problems with peptides, or one of the interesting things about peptides, is a very large space of peptides that we can look at. So just some examples of peptides are like FF, which is one that self-assembles, RGD, which is one that binds to, what is it? Epithelial cells? I forget. I'm losing my touch here, guys. And then this is a peptide which self-assembles into a non-fouling interface. Is just a little picture showing what a peptide looks like. So maybe you're familiar with proteins like albumin. Peptides are typically smaller. They're on the right. So the peptide for our motivating example is A beta, which is hypothesized to be related to Alzheimer's, hypothesized to cause Alzheimer's. And it's hard to simulate this whole peptide. And so one of the things we can do is look at a fragment. One of the fragments you can study is 21 to 30. There's a lot of different fragments of this peptide to look at. One of the challenges is that when you cut out a fragment of the peptide and you want to study it, you're no longer sampling the whole peptide. So one of the questions is, how can you learn anything interesting from looking at the fragment? And this is one of the applications of experiment-directed simulation or these biasing techniques, is that although we can cut out this fragment, this 21 to 30 fragment, we're only going to look at the part here that is colored in. We can bias the simulation to look like the whole fragment by using experimental data. So that is, we're going to look at just one fragment, but what we can do is put in the chemical shifts that we know come from the whole assembly. And that allows us to sort of, rescue the structure, or allows us to sort of bias the system to look like it's in the larger unit. So that's one of the interesting applications of this method, is that although we make approximations like removing, counterions, we remove glycosylation, we cut up the thing into fragments. One of the things we can do to make sure we're still connected to experiments is use experiment-directed simulation or other biasing methods to ensure that we agree with the observables. Okay, so that's just a little bit about why we're looking at a peptide. So when we run the simulation of this peptide, I'm showing you here over time, and on the y-axis is the average disagreement chemical shift. So that shows that when we run the simulation, the peptides don't have the agreed chemical shift. So there's some disagreement between the experimental data and our simulation. And this is common, it's hard to get all the chemical shifts correct. So then the idea is now we're going to make the observable be an input. So what we're going to put in our plumed file is the known observations from NMR. And the idea is that once we agree with the chemical shifts, then we can measure other quantities of interest, like maybe we can look at the structure or the diffusivity, something like that. So it's I think it's an unusual way to think about setting up your simulation files, is that instead of just putting in the potential and the initial structure, we're going to also put in some observables into our plume file so that we agree with the experiments. All right, so the way that we do this, the way that experiment-directed works, is that it's formulated as a maximum entropy method. So if we have our original model here, and the original model being our original molecular potential, there are many ways we could change this model to agree with the experimental data, right? We only have like 3 or 4 experimental observations. And our potential energy has many, many more parameters. So there's lots of ways we could change our potential energy to agree with those 3 or 4 data points. And that's represented here as this large gray sort of manifold. These are all the ways we could be consistent with those 3 or 4 data points. So we want to throw in an extra constraint. And that extra constraint helps us sort of go from this degenerate possibility to a unique solution. And that is going to be this blue one here. And so how do we set up that constraint? We say it's the closest distance. And how do we measure distance? Well, we can view the original model as a Boltzmann distribution with the original potential energy. And then we're going to change that potential energy, which changes the distribution, over to here. And we can use relative entropy as a measurement. So relative entropy is a way to compute the distance between these 2 systems, two potential energies. So this is a Lagrange multiplier problem, actually. So I'm showing it a little bit better here. So we have the original probability distribution P naught, then we have P prime, our new probability distribution. It's constrained to agree with the experimental data. So that is, it's going to have the observable S of R be equal to S hat, where S hat is our, I'm sorry, I have to go let my dog in. I'll be right back. Okay, sorry. So then what we do is we bias to agree with it. So it's a constraint. The constraint is that we agree with that observable, and we're trying to minimize or maximize it. In this case, we're trying to, oh, maybe this is a mistake to let my dog back in. Siggy. So we have delta S rel, which is the quantity we're trying to minimize. And you can just set this up. It's a fun little math problem of Lagrange multipliers. And it turns out that the way to bias the simulation, the way to bias your ensemble to best agree with the observed data, is a linear constraint. So we add the observable directly to the potential energy. Now, what's unusual about this is that when we add this f of x term, or the f of r, or s of r, as I've changed notations multiple times here, but the collective variable is added here, you have to put a little term here. And this term here is chosen so that you get the agreement. So what's interesting is that no matter what value you're trying to agree with, no matter what the chemical shift is or what the radius of duration is, you have to set this little value here, this alpha value, to get that agreement. So it's an iterative solution process. So that is, we start the simulation. We don't know what this alpha value is. And then what we do is we run the simulation for a little while, and we can get a better estimate of this and a better estimate of this. So it's not something you can analytically compute. So the bad news is that this has to be computed as you run the simulation. The good news is that we've solved this generally. We always know what is the maximum entropy or the minimum relative entropy solution to the problem is always to have a linear bias or a linear constraint in our system. I guess I should say linear restraint. So we know that the linear bias is minimal and unique. I'm not talking about it here, but you can show that it's mathematically unique. However, there are many, many other ideas about how to minimally bias the system. So I have here this nice 2017 paper that looked at many other methods, and this is old now, 2017. So there are many ideas about how to minimally bias the system. And in Plume, there are multiple modules for this. I believe there's a module called Maxent, which is in Plume, which also does the same thing. So let's just take a look to see what this is, to get a sense of this. So in blue, I'm showing you a unbiased probability distribution. So this is the P naught in the mathematics above. So you can think about this as just the free energy. So this is the negative natural log of the potential energy. Sorry, e to the minus potential energy. And I'm showing you that my system unbiased has a mean in this vertical blue line. And what I'm doing is the vertical dash green line is my experimental data. And I'm showing you how to move from the blue to the green to change what the experimental data is, what the observable is. So the mean is shown here in blue, the mean is shown here in green, and we're modifying our potential energy to agree with that. And down here, I'm showing you what is that alpha value. So you can see that as alpha moves, we get one specific vertical line. Oh, don't let the dog out. Oh, okay. All right. So how do you do this? Rowan, where's? Okay. All right. So in EDS, sorry, to use this in Plumed, all you need to do is set your collective variable. So here, like this, and then you just call the EDS module and you set what you want it to be. So you define a collective variable, and then you define what you want the experimental data to be. So experimental data here is 2, and then the CV here is distance. So I'm just going to talk really briefly about how you actually find this alpha, this Lagrange multiplier here. So when we are running the simulation, we basically can estimate, we'll use gradient descent, so we can estimate the partial derivative of the agreement here. So this is how close we are to the experimental data. We can compute the gradient with respect to this alpha term. So this is just gradient descent. It turns out there's like a nice little mathematical proof you can do that this gradient, which looks really intimidating, right? Because this is like how the ensemble average changes with respect to a linear bias in the potential energy. It turns out it's just the product of the mean deviation by the mean variance of the deviation. So this is like how much we agree with it. We take the mean of it. Then this is the variance of the observable. So it's just the product of the mean and the variance, basically. So just a minor detail is that to get this to work in multiple dimensions, all we did is stochastic gradient descent. So we compute these gradients, this gradient here, we compute this for every collective variable being biased in the system. And then we just randomly select some subset. So if you have 5 collected variables, you have 5 gradients or 5 partial derivatives, and then we just maybe select 3 of them or 4 of them or 2 of them at a time. And that sort of helps us get avoid local minima as we try to optimize these steps. So just a little bit of nomenclature. So why is it called experiment-directed simulation and not maximum entropy? Well, that's a very good question. But basically, when we're running it, like as in we're trying to adjust the alpha parameters, we call it EDS. That means that we're changing the bias as we run it to adapt to the observable. And then once you are done, once it's frozen, that's when you have this maximum entropy bias. So when you have this linear restraint and it's no longer changing. So just, there's 2 kinds of ways you can do this. You can, as you run it, be adjusting alpha to where you want it. And then once you have it, you can sort of freeze it in place just to have that linear restraint. Okay, and then just to show you that this works, here is that simulation I was showing you before. On the right-hand side was the collective variables were just not agreeing with experiments. And then on the left-hand side, we can see that the collective variables now agree with experimental data. So the y-axis, remember, is how far off we are from experimental data. So obviously with EDS, we agree with the experimental data quite well. So just as a reminder, you can compute chemical shift in PLUMED. So that's how this is connected back to PLUMED. Just to show you a little bit more about this. So the idea usually is that we agree with experimental data on some collective variables, but it's not really meaningful to then analyze those collective variables, right? Because we set their values with EDS. So we'll usually look at other properties in the simulation. So here I ran this peptide simulation, and you can see on the left-hand side, our Ramachandran plots show there's a change in the occupancy of the dihedral angles. And on the right-hand side, this was the normal simulation. So we can see there's some change as we agree with the experimental data. Then we can go to more fragments. So we basically did 1 fragment in that simulation. We can also do 4 fragments now. And the idea is that by biasing here, when we have 4 peptides, we can start get closer to the self-assembled structure of this peptide. I won't go into it too much, but basically what was interesting about this work is that when we had 1 peptide and we biased it, it looked very similar to when we have 4 peptides. So this over here on the bottom right, this is 4 peptides with good sampling, and this is 1 peptide with the EDS method. So we can kind of see that we've approximated the structure by putting in information from the experimental system. So it's kind of an interesting idea that you can kind of get at self-assembled structures by using experimental data from the self-assembled structure, but still just doing a monomer simulation in MD. And then we also did like a little bit of structural analysis in this work. So one of the checks on all of these methods.
When I had to, but baby,
I know.
Mommy come in.
Mommy's getting the dog right now. Okay.
But Siggy, we are now.
Okay. Why don't you go look to see if you can find him? Okay. So one of the things we like to do is we want to check an independent measurement to make sure that we have agreement. So one of the things we did in this paper was that we used EDS to sort of repair the structure or to get better accuracy on the structure. And then we did a diffusivity measurement. So we can compute diffusivity from the simulation.
I found Siggy.
Where is he?
He was outside in the.
All right, Ron. Let me just talk to my friends for a little bit longer, okay? Thank you.
Okay, but.
Okay.
I'm done with this.
Okay.
You still have to eat.
Okay, I'll eat the rest. Thank you, Ron. So we found that the diffusivity agreed with the experiments after doing the biasing with EDS. So you can read more about this paper here, but basically EDS helped us get better accuracy of the structure, better agreement. Yeah, why don't you go see mommy, okay? Okay, great. I'll just mention that EDS, as we'll talk about it today, is for making scalars agree. We have another method, which is in PLUMED, that allows you to match distributions. It's the target keyword in metadynamics. And then the maxent package in PLUMED helps you deal with experimental uncertainty. And you can also extend EDS to deal with experimental uncertainty as well. So it's in Plumed, like I said. I'll just mention quickly that, this is just a high level overview of the method. Giovanni wrote a nice paper on how to deal with uncertainty with max-extent methods. Glenn wrote a paper and he'll talk today about using this with coarse graining. Thomas de Lafage also did that. We wrote a paper down here on how to deal with MPT. And so there's a keyword virial in Plumed to basically minimize the change in virial when you're using this method. It's like a mean field method in coarse graining. You can combine it with enhanced sampling. So in the work I just showed you, we were using parallel tempering well-tempered ensemble, which is enhanced sampling method. And then you can work with probabilities, like I said, and we've used it in many, many systems, including density functional theory, ab initio, MD. And it seems to be a pretty robust method in all these areas where, when you improve the accuracy in one collective variable, it seems to improve accuracy in other collective variables. Okay, whew. So with that, I'm going to turn it over to Glenn, and he's going to talk a little bit more about the method and in coarse graining. Thank you.
Okay, yeah, thanks, Andrew. And I can also show the examples. I opened that up after, if it's easier. So I'm going to talk about this paper I wrote with Thomas Denenhofer-Lafage that Andrew just mentioned, called coarse-grained directed simulation. And it's actually the same method, it's just a different application. And we also made some changes to the implementation in this paper that I'll talk about. So the motivation of what I was of applying EDS was that we wanted to study actin, which is a large single domain protein that forms long polymers. So here you can see in the ribbon diagram, one actin monomer with some other ones vibrating around it. And we wanted to understand or develop a method where we could, kind of like QMMM, where we could treat the central actin atomically and the outer domains in some coarse-grained way. And in this particular paper, we didn't go to that limit. What we did instead is I realized we often think of this central monomer as having 4 big coarse-grained domains. And I wondered, could we bias coarse-grained observables to match what they are from a fully atomistic simulation so that we could just simulate a small subsystem and use that. And the reason, so here I'm showing that inside of a filament, if you just look at these 2 coarse-grained observables, the dihedral angle and distance here, angle between these 4 beads and the distance between 2 of them, it's very flat and stable. And if you take it out of the filament and you run it, it has a different twist and distance. And this turns out to be really important for the hydrolysis of this ATP molecule that I show in here, which changes its hydrolysis rate by orders of magnitude, or actin catalyzes hydrolysis by orders of magnitude when it flattens as it enters a filament, which serves as an important timing mechanism. And so other people in the Voth lab at the time were doing QMMM calculations on a single actin monomer to get these profiles that you see here, including Ray Sun in this particular paper, and Martin McCullough in an earlier paper. So what was the issue? The issue is that outside of this filament, you have to restrain the actin monomer to stay in this conformation. So otherwise, I found if you just let it go, you'll see that it spontaneously twists and opens up, which is kind of what you expect because there's no reason for it to be in that conformation when it's just floating around. So in that paper, they added harmonic restraints, which we'll see is not always a great idea because it changes things. And so we wondered, could we use this EDS method to bias the system to look more like these blue lines? So in other words, what we would need is to shift these lines back to where to these other values for an unrestrained, or for a previously unrestrained system. And also, if you look at what's going on, you'll see that the variance of these data is different between the blue and the red lines. So we also need to correct for the fact that when it's not in a filament, it's fluctuating more, and we need to dampen that somehow. And so we thought we could use this EDS method, which Andrew just talked about. So we would learn a couple of parameters that would keep that in place. So this is just a slide of what he just talked about. Okay, so this coarse-grained directed simulation means that it's not about coarse graining per se, it's about using coarse-grained observables and biasing them to match other values, which could be experimental or from other simulations. So to remind you again, this is what a filament looks like, the target, and the bottom is what happens if you, well, it's what happens if it's unbiased, and also what I'm actually showing here is when we just turn on the EDS method the way that Andrew just talked about it, it did not work. So what's going on? Why doesn't this work, even though Andrew showed that it works very well for a lot of systems? So the challenge was when we switched to this atomistic system that convergence was very slow. And just from a physical point of view, something you might want to think about is a lot of the systems Andrew had applied it to previously were liquids like water and Leonard-Jones fluids and so forth, where every atom has an environment that you're biasing. And so it has a self-averaging property, which we often see for condensed phase systems. The other thing is that the time that we need to sample the bias parameters could be, tens or hundreds of nanoseconds. So we need to be as efficient as possible in learning these parameters. And so what I did to try to improve the method is I actually first started with a coarse-grained model. So this is a 12-site elastic network model that represents actin. And actually, if you want files for this, you can find it in the Plume nest for this paper if you want to play around with that during the exercises. So the first thing I did is I ran this elastic network model and just biased this dihedral angle to see how different parameters in the method affect the convergence. So first, there's a amount of time to sample that you have to choose. And I found that if you shortened it, for example, it actually sped things up a lot. And if you shortened it more, it sped it up even more. And if you get too short, then it doesn't have a good estimate of the value you're trying to bias. So that went bad. And so there's sort of a Goldilocks situation where you have to make a guess, but also try to optimize your, your pace in order to get the quickest averaging, which is something you can try out in the exercises. Now, next, in order to represent the filament properties, what I wanted to do was bias this angle and distance and also the variance of the angle and distance. And so for the stochastic gradient descent method, I was able to do that for this elastic network model with this shorter time, and it worked okay. But I wanted to be as fast as possible. You can see that this is, maybe this is, I don't know if this is atomistic and it's sort of working, or this is a long coarse-grained simulation, actually. Forget now. But this is long, this is slow, so that's not good for the atomistic system. That would take, 100,000 atoms, that would take, a couple of days to simulate maybe, so it's no good. So Andrew told you about using stochastic gradient descent to use a batch of variables. And in this particular case, what we realized is if we can also replace this gradient of a single one with a gradient of the whole vector. And in that case, this term, instead of being the difference and the variance of a single vector, you get the vector distance and the covariance of the term. And so there's an option in EDS called covariance, which will do all your variables at the same time using this regular gradient descent, not stochastic gradient descent. And so when I turn that on for the system, you see that it makes the convergence time for this system, 5 times faster. So that was nice. Then when we were talking to some mathematicians who, think about optimization a lot, they said, why would you do gradient descent when there's this other method called the Levenberg-Marquardt optimization method, which is interpolation between Newton's method and gradient descent. And all we really had to do to change that was to change the prefactor of this term, which is all, and so that's another option, LM in Plumed. And for this particular system, you see now we get another 5x speed up of convergence. So then, and by the way, just to mention one other paper that wasn't in Andrew's talk, in a follow-up to a paper I worked on with Andrew on biasing ab initio water, Paul biased a different variable where convergence was really bad, and we had to use these Levenberg-Marquardt thing to even converge within the tens of picoseconds that we could afford to simulate for ab initio water. Okay, so now going back to the fully atomistic system, I was able to, in tens of nanoseconds, bias a single atom actin monomer to behave like it's in a filament with the correct variance and average. If you look at the convergence or just the structural difference between actin starting here and ending up here, it does go down, which was good. So as Andrew mentioned, you bias some variables and you have to check if other variables also improve. But it would be nice if this was a little bit better, but this is what we got with just biasing these coarse-grained observables. So it goes down from 5 to 3. But it turns out from my experience since then, it's a very subtle structural change that's hard to sample. So that makes sense. Now, one last thing I wanted to mention from this paper is that we also tried biasing a larger subsystem. So in this result, we biased the angles and distances of all 3 of these monomers. And you can see that over time, all 6 of these variables match the target values, but we did not bias the variances. And interestingly, they found the correct values of variance by themselves because they're interacting with neighbors. So it's something to consider when you're choosing what variables you want. If you're doing some protein system like this, if you can have it in context and include some allostery, then maybe you have to do actually less work to bias the system. The last thing is related to that last, if you see what happened here where things actually start to twist and get out of line and eventually the biasing method is able to push it back, is that, and by the way, this is showing that happening and then continuing with the freeze mode of EDS where it keeps the parameters on. From a conceptual point of view, what I realized at the end of this paper is that EDS or maxent or whatever can be a great method, but it's really tricky in the situation where you actually usually expect to be, which is that you're close to the target value at the beginning. So if your free energy surface looks like this, and you start close to the target value, like so you're able, in our case, we're able to take an actin filament that's close to the filament configuration and start there. Then when you start doing your EDS averaging, because the parameter is proportional to the difference between your current average and the target average, you will estimate a parameter that's close to 0. Then all of a sudden your system will figure out that which is unbiased, that it can get somewhere else. And then the method has to work really hard to push it back. So this is kind of the challenge of using maximum entropy methods. A challenge if you're starting close to your target value, but there's another more stable state somewhere else that you want to prevent. And I don't know if anyone solved that challenge since, but maybe we thought about in the paper, maybe you can sort of start with a harmonic restraint and then slowly turn it off while you turn on the maximum entropy restraint or something like that. But it's something, you know, that you guys can think about. One last thing I remembered while Andrew was talking is, I don't know if I can go back to the original method, his slide. Yeah. So Andrew did say that there's no way to predict these parameters without estimating them from the simulation, which is true. There's no analytical formula, but in the CGDS paper, we do write down what you can also prove fairly easily, which is that in the limit of small lambda, you can, there is a solution for what lambda should be that gives you the shift in average, which is, if I remember correctly, something like the difference in your mean from the target value divided by the variance or the squared difference average with a minus sign. And so you could start from that. It's a good guess, which you can calculate very easily from your unbiased simulation and then plug that in as your starting value. But we didn't even have to do that for the Acton paper, so we didn't worry about it too much. Okay, so I think if you want, Andrew, I can do it, the examples, so that it's less interrupted. So we just wanted to show you a few, the bit of the implementation, which, as Andrew said, so of course I should say Andrew was, he's being modest, but this idea was out there, but Andrew, I believe, was the first person to come up with a practical way to do this in simulation in around 2014 or 2012, I guess. And but then we worked on some papers together, and Andrew wrote the original implementation in PLUMED 1.0, and then we worked together on the EDS module for PLUMED 2.0. So this is what it looks like in PLUME 2, which you're all familiar with. This is an example biasing the distance and the squared distance to two different values using EDS. And then you can, print out the distance, the squared distance, how hard the coupling for each variable gets an underscore coupling. You may be familiar with some things like that, which is that alpha or lambda parameter. And then there's the total bias applied and the squared force, which you can print out every so often. You can also fix a bias, and you can ramp up to it like linearly in case you know what your target value should be, or you just want to choose some other linear bias. So that's what's in this one, right? You can, if you want to continue or use the final value of a biasing parameter, we have a restart file format that we wrote. And so then there's an out restart and an in restart. The restart file looks like this. It has the values of your things versus time, the coupling parameter, which is that alpha or lambda, some things estimated, which it can use to the maximum prefactor that it can change. There's some, minor technical things to the stochastic gradient descent, which are in here so that you can restart exactly. And then you can read it in so that you can continue your simulation. And you can also, as I alluded to in my talk, you can read in that previous restart, and it will just take the final line and keep that value. The mean from the previous simulation. So I guess this takes a certain, rather than the final exact value of the bias parameter, which is a little bit random because it goes up and down, it takes the average over the previous thing. So you could do like run for 10 nanoseconds, then run another couple nanoseconds, and then take the average of that previous file, I believe. Yeah, makes sense. And oh, is this the same thing? What's the difference here, Andrew?
This one basically restarts EDS with the mean of the previous one.
Oh, I think it's not supposed to have freeze here, but it's probably what you
maybe
mean
something
then.
like that. Yeah.
Okay, so take out freeze. Sounds good. Okay, so those were our examples. In the work through that I'm going to show, the tutorial we made, I actually meant to, but I didn't put one with this freeze example, but I said it's something you could try out, and it is something that makes sense to try. And just to point out a reason for that, and Andrew did say this, that you're learning a new potential energy surface, which just has this linear shift. And so once you turn on freeze, you now just have a linear shift to your potential energy, which you could also do with the restraint function slope if you wanted. And then you can do any enhanced sampling method on top of that, which Andrew did mention, because it's just a regular equilibrium free energy or potential energy at that point. And so just to quickly show the, okay, here we go. The first, here's the manual for EDS, and there was one other technical point, which Andrew didn't mention that was important, which is that in the original implementation, the default was to divide the observable by the target value. And that was to do a bit of regularization. so that, the energies wouldn't be really big or whatever. But that got to be a problem when we wanted to bias the observable to be 0 or various other situations. And so there's a scale factor bias scale, which you can set to be 1. And in the tutorial, or in the masterclass tutorial, I just set bias scale to be 1 in general. Otherwise, you'll find some interesting results, which you can play around with as well. Now, over in this masterclass module tutorial, we have a little reminder about this. So as I said, if bias scale is 1, then it will look like this. And all you need to, we'll have to check this. Yes. There is a GitHub page that I made for this, which has some example inputs for the PESMD feature, or potential energy surface molecular dynamics feature of PLUMED, which you all have if you have PLUMED installed, and then some inputs for alanine dipeptide that I borrowed from the last masterclass. And, oops, am I in the right? I'm in the wrong window, right? There we go. And then I have a little bit of some exercises to work on. So the first one is a single harmonic oscillator. And what you'll be able to check really fast is that when you apply this linear bias that's learned, you can shift it to any new mean that you want, but it won't affect the variance in the same way as applying a restraint. So I show that versus time. I'm going to fix these pictures afterwards. And you'll see that you can shift the mean without really changing the variance, whereas if you apply harmonic bias, as was done prior to my CGDS paper that I mentioned, it will shift the mean, shrink the variance, and actually you'll find, and it makes sense if you write it down analytically, that with the harmonic bias, you'll never reach the target mean anyway. So it's not the best way to achieve your goal. Then you can check how the scale factor converges and whether or not you understand what bias is being applied, and then move on to a double well potential where you now have multiple variables you can do. You can shift it to the right, you can shift it up and down, or you can change averages or combinations of X and Y. So I just chose one that you can try. And then for alanine dipeptide, this is what an unbiased simulation looks like. You know that really there should be some more stuff around here that are metastable states, which you can't reach without metadynamics or umbrella sampling. But interestingly, if you shift it so that the mean of phi equals 1, then all of a sudden you jump over to that state. And if you shift it to the mean of psi is 1, then you have an unusual potential energy surface if you're used to looking at this alanine dipeptide. And then finally, because we didn't want to burden you with too much, but if you have a different system that you're interested in, we strongly encourage you for the final part to take your protein and try to bias 2 or more observables at the same time, protein or liquid system or whatever you want, and see if you can get it to converge and shift the mean, and tell us about it next time. Okay, so I think that's all that we wanted to say.
I'll just mention one thing, Glenn, is
yes,
in EDS, there's as Glenn mentioned, there's ways to speed up convergence, like adding the LM or the covariance. The period, though, I think in the range are the #1 places to start. The period being how long you try to estimate the mean of the variance, and then the range being how strong are your steps. But then, of course, if that doesn't work out, then you can start trying these more sophisticated methods. I'll mention one other thing is that if you have lots of correlated collected variables, so like if you're trying to bias the mean, the variance, the third moment, the fourth moment of one particular collected variable, you can often have like a problem where the bias just gets higher and higher and higher as it tries to get all these correlated ones. And we found that if you add the virial keyword, which is this basically regularization to EDS that causes the bias to try to stay low so it doesn't affect the pressure as much, you can put that on, and that'll help sort of reduce the bias exploding. So if you ever find that your bias is getting too high, or your system is exploding, or if you are doing NPT, the virial keyword is a great way to sort of clamp down on the bias so it doesn't just sort of run away. And then as Glenn mentioned as well, and we've written multiple papers where you also do enhanced sampling to get at this problem Glenn was mentioning, is that if you're stuck in some local minima in your collected variable, you can always do things like replica exchange, you can do parallel tempering, multi-tempered ensemble, any sort of these enhanced sampling methods that don't target one CV, that just sort of broadly enhanced sampling. They're really good to use with the EDS, because EDS needs to be able to estimate the variance of the collected variable across the whole range. Oh, thank you.
Yeah, thanks. And I don't know if Giovanni has any comments on his implementation that he wants to throw in, because another thing you can try, which we mentioned in the tutorial a little bit, is if you want to try the max-n keyword, you can probably see if you get the same results and do some debugging for us, stuff like that.
Yeah, you can try. The features are very similar. Maybe there's something different. There are maybe less of these optimization schemes implemented. We only added the stochastic gradient descent. On the other hand, there's more flexibility on what you can do with replicas. I think you can, for instance, have multiple replicas, train lambda or alpha on one replica and use it on the other replicas. So there are some technical differences which are mostly historical due to what we needed when we implemented it. But you should be able to figure out how to map the parameters looking at the manual, and basically do, for this simple exercise, I think you should be able to do the same. It's a good exercise to do it.
Exactly, yeah.
Great. Any other questions or comments? So Andrew and Glenn, anything else?
Yeah, I just opened it up for questions. If anybody had any questions about the exercises or the method.
And yeah, we'll be happy to answer questions in Slack as well.
Yeah, actually, one comment is that if you want to join the Slack channel and if you want the Zoom link for the correction next week, please fill the form that I sent on the chat.
I'll mention as well that we wrote a review paper. It's on the slides. And I think it's in the, maybe we'll make sure it's in the tutorial, but we wrote a review paper as well that covers all the different methods and extensions of EDS, and also gives some details on some of these more sophisticated things like adjusting for the virial and biasing without certainty and biasing to distributions.
Okay, great. So no questions from the audience. So maybe we can close here. So then thank again to both Glenn and Andrew. And then, so remember that they will be available during the week to answer your questions on Slack. So don't be ashamed. Ask and yeah, do your best to take advantage of their availability. And then, so thanks everyone and see you next week.
Thank you.
Bye-bye.